As I told you, I'm working for EMSIS. EMSIS is located in Münster in Germany and was founded about 5 years ago as a buyout of the complete EM imaging solution section of Olympus. Extended by a sales group in Asia and supported by a global network of agents and authorized sales partners, we serve our products to a worldwide market. EMSIS today can offer a complete lineup of TEM cameras, starting with a 2.8 megapixel side-mounted camera MegaView G3 and end up with a 20 megapixel CMOS-based button-mounted camera Xarosa. All these cameras can be fitted to nearly every TEM, the retrofit and also the new column business. All the cameras are served by our own imaging software, Radius, which is not just supporting the excellent features of the cameras, is not just an imaging software, it is also offering measurements and also analytical tools like the particle detection I'm going to talk about now. Among offering installation services and support on our own systems, we are also the German distributor of Nanomegas, a well-known supplier of excellent hardware and software for specific diffraction analysis tools. Let me first start with a short introduction to the topics of this webinar. Every particle counts, radio solution detection, particle separation and detection on TEM images. I will start with a very short introduction into the particle separation itself, just to let you know what the basis of this are, followed by a step-by-step introduction into the needed steps to process such a detection. It starts with threshold setting, a very decisive process, continued by the particle detection process itself, followed by obtaining the results by means of particle measurements. And if you like to, you can do a further classification of the results and even compare these results later on between different areas on your image, the so-called regions of interest or ROIs. If you have a look on the images which are popping up here right now, the first idea is that it's very easy for the human eye to detect objects on these images. They are really different, but there is no problem for the human eye to directly approach these as objects, as particles, and there is no real big problem for you to, for example, count the black particles on the upper left image or even see the smaller dark objects in the lower left image. Even in the image here in the middle where you have some concrete, you can identify different gray values, and it's easy for you also to separate white from gray particles. Which is quite easy for you because you're trained on this. Is very difficult for the software because every element on such an image is having the same level. It's just a picture element on the image itself. Again, here the immunogold labels you can see here, very easy for you to count. But if it comes to a larger number of particles or a large number of images, it would be very suitable to have a tool at your side who is doing it more or less automated for you. And I would like to show you a process in the following slides on how this can be achieved. If we have a look onto this very simple immuno-labeling image, it's an 8-bit gray value TIFF. And again, here I can look into more detail. I have an isolated particle, and it's obvious here to see that a digital image consists of pixels. And these pixels are defined by the XY coordinates and by an intensity value. So it's nothing more than that. Very simple image. The XY coordinates you can see here in the tool, and we see a corresponding intensity value. So basically for the software itself, the image looks like this one here, right? Just for us, we notice that in the central of these numbers, there is some lower intensity values, and we can use this knowledge to separate the particles from the background. The software is seeing this as intensity values, but we can make use of an 8-bit lookup table to assign for each intensity value a certain gray value. You see here the lookup table for every possible intensity value starting from 0 up to 255. We have a certain gray value applied to an intensity value, and this allows every imaging software to display your image in the same way as a gray value image. But all these numbers are of the same level. The software cannot identify on its own where is a certain object of interest and where it's not. So we need to have a tool on our hand to get this information. At first, I would like to give you the overview on what we are doing right now. We start with a histogram-based separation of gray values into foreground and background. A very decisive step in this process, and I will go in more detail on that. The second is the evaluation of detected objects by means of particle parameter. It's a kind of preparing the results, and these results can be grouped into classes based on one of the particle parameters chosen before, like the size. And if you like to, that's an additional option. You can compare the results you have obtained even between different regions of interest on your image or between different images. Coming back to the histogram-based threshold setting, a histogram, like we use it here, is a graphical representation of the gray value distribution of all pixels on your image. It just plots the number of pixels for each gray value into this diagram, and it gives you a characteristic shape of your image. You can easily identify two maxima here, one to the more brighter part and one in the more darker part. What you see here is a histogram of a 16-bit image. It starts with 0, which is always black, the darkest value, and it ends up at 64,535 as a total white pixel. And you will find your image information in between here. Most of the software dealing with 16-bit images will only choose the area where you have pixel information to display on your monitor. So you have the dark values, the middle gray, and the white one. At a given position on the x-axis, where you have listed all your pixel intensities, it just plots the number of pixels sharing this gray value. So this is your histogram of the image. If you have an 8-bit image, it looks a bit more simple. You see we have just intensity values from 0 to 255. But what you can also easily see here, the separation between the huge bright area compared to the dark one, where our objects of interest here are, is less good. So most of the times you can have a more effective separation on a 16-bit image. So I'm switching back to that. What you can also see here is a minimum between the two maxima, and this is always an indication that such an image is very suitable for a threshold-based separation of particles. This will be today's image for the detection process. It shows a double labeling experiment on a biological tissue. The gold labels are linked to an antibody, and this antibody can be bind to certain biological molecules such as protein, as on membrane proteins, for example, and this makes it very suitable in electron microscopy to detect certain structures on your tissue. The gold is electron dense, and thus it's an excellent tool to use threshold-based particle detection on the image. Zooming into more detail, you see what already reading the histogram was shown. We have a nice separation of a given particle to the background, and that should be very helpful later on for our process. Also here I can display the intensity values, and there is a clear border from the particle of interest to the background. Nevertheless, it might be very difficult to find the right value using just these two information. That's why we're using another tool. We use a histogram, and this special histogram allows me now to select here a ruler to define in a very accurate way my threshold. And while I'm moving this ruler to the left or to the right, my preview here on the image will change, and I can directly see to which level I need to go to have my best separation of the particles of interest to the background and not to detect too much of the background. You see here already I'm absolutely at the border. The first particles which seems to belong to the background are already detected. But to cope with this, I will give you later some ideas. So that's the very nice tool to use. And if I confirm the setting, which means I'm applying the thresholds, I'm creating internally a binarized image. The binarized image has just two conditions, black and white, where the white pixels are detectable and the black pixels are belonging to the background. And now I placed into this image a level which allows the software, like the human eye can do easily, to separate between structures of interest and between background. Nevertheless, for your convenience, and that might also be very helpful to see the labels on the tissue structure, you are working all the times on the gray value image. It's just internally processed, which separates this image, and from now on, you can use this as a base for the following steps. So histogram threshold setting, very decisive, and sometimes it is also needed to do some filtering of the image to have such a nice separation shown in the image here on the slide. The second step is to prepare your detection process itself. There are several criteria you need to check and you need to consider to make it a really successful detection. I listed here 4 of them: the pixel connectivity, the detection area, the border particles, and also how to deal with holes in your particle. Coming to the first, the pixel connectivity. This is a parameter which let you decide how accurate you would like to separate your particles. It's very much depending on your analysis task, what you should select here. If you just choose advanced borders, only the direct neighbors of a pixel will be taken into consideration to decide if the pixels belong to one particle or if they should be separated into 2. And if I go to the opposite, to the include diagonals, already the single bridge here between those 2 pixels are enough to make the decision that all these pixels belong to one particle. You can now easily see that here it is quite important to choose the right value, because this could be 2 5 nanometer labels, but it could also be 1 10 nanometer label, right? So it's quite important here. And typically, if you like to have an accurate separation, you should always use only advanced borders. Right. The detection area might be very important as well. Quite often you can use your whole image for the detection process, but sometimes you have unwanted areas which should be not taken into consideration. Very often, I have to admit, you have a grid bar in there, and then it's quite nice to restrict your detection process to a certain part of it. Instead of using the whole image, you can define a rectangular area, a frame in your image, and automatically the detection process will be restricted to this area. But it can also be more complex. You can also use a drawing of any kind of a polygon to have an irregular shaped area of interest and to limit your detection process just to this area. This is all defined before you start your detection. The third criterion is how to deal with border particles, especially if your size is of importance. Border particles should be excluded if you are detecting on the whole image, because you have no idea how big the particle might be. If you are working with a frame, you may decide if you would like to totally include or exclude them. These three options are available. I was choosing here just a circle as the region of interest. Truncate means we will simply take only the part of the pixel which is inside the area of interest. Exclude will exclude the particles completely if they are touching the border. And include is just the opposite. The particle will be included with its total area, even if part of it should be out of the area of interest. And finally, we have a minimum size filter and a feature to work with holes and particles. A minimum object size filter can be very effective. Quite often, the setting of your threshold value is critical. So you will have some spray pixels everywhere in the image sharing the same gray value range as your particles of interest, and then it's very successful to set a minimum of that. We typically say if you would like to do particle detection, a particle should have at least 20 pixels to build it up to be accurate in the results. So a minimum object size of 10 pixels should be really fine here. The same is true with holes and particles, which is not very often true for gold labels because they are electron dense and they typically have within the complete particle the same or very similar gray values. But on larger particles, it might happen that because of your threshold settings, you will create some holes in your particle. But as soon the whole particle is surrounded by one pixel line of your gray value, you can just click here on fill holes and it will fill the holes and you can grab the correct area information from such a particle. So these steps were all taken to prepare our detection, and now we are talking about which kind of results we would like to get during this process. We have three different levels of measurements: the object measurements, class measurements, and the highest level, the region of interest or ROI measurements. Object measurements are applied to every single particle, and the class measurements are applied to group particles belonging to one or more classes. And the ROI measurements are applied to regionally grouped particles. So three different levels of measurement or parameter which could offer you later on the results. Coming to the object measurements, you select your parameter of choice at first out of the huge list of different available parameters. There should be one fitting to your request. For detecting the immunogold labels, the equivalent circle diameter turns out to be very effective because, as you can see here in the pictogram and also with the explanation below, it counts the diameter of a circle which has the same area as the detected particle. So if you have somehow an irregular shaped particle, you nevertheless can balance this a little bit by using the ECD value, which gives you a kind of a mean diameter of such a particle, depending only on the area and not that much depending on the shape itself. So after having it added to the list of completed measurements for all objects, you can give it another sequence, which just alters the sequence of the measurement results later on in your resulting sheets. We have the option to save all our settings in the configuration file. This is very nice to have later on a more or less automated process, but you can also offer your settings to other people, make it in public, or just for use it for other experiments on your own. All the parameters you are selecting here can later on be used either as a base for the classification or to use object filterings. We come to that in more detail later on. The class measurements now needs to have a classification scheme which needs to be created first. I will come into this in more detail in a few minutes. Now I would just refer to the measurements. You select parameters for a class like you do for the object measurements. It can even be the same parameter as you can see here, but instead of getting now a single result for a given particle, you can, for example, here get the mean value of all detected objects belonging to this class. Even here, it allows you to get not only mean results, we have also a parameter, a class parameter here, which allows you to count the objects. So just with one mouse click later on, you will be able to see not just the mean results, but also the number of particles belonging to this class. And also here, it can be saved in a configuration file, which can be used by yourself or by other people later on. The raw measurements now allows you to compare object and or class results between different regions on your image. Also here, you can get mean results for the class, and also here you can do a counting, which is now specific for a defined region of interest on your image. And the same here, all configurations can be saved so that you just once need to do this configuration, and later on you can just load it. All right, so this was all kind of preparations we need to do at the very first time. Later on, we can just make use of it. And we can grab our first results. So far, I did not create any classification scheme. So my first result will be object measurement. They all belong to one class. They have one color. And if I have a look onto my most important particle parameter, ECD, equivalent circle diameter, I get for every particle detected, I get the results. And below I see also some basic statistical values here. They are counted, and I get also a mean value. The mean value here for me is without any use, because my goal would be to do a double labeling analysis, and so far this would not be possible. So what I need to do is I need to create a classification scheme, and my goal is to create two groups, one detecting the 5 nanometer and one detecting the 10 nanometer gold. The software offers me a nice wizard that allows me to define a new name for a new kind of labeling, and I'm selecting here 1 or 2 parameters to define my classification process. For now, I will use the equivalent circle diameter. And again, you can see here the software offers me a histogram, now not showing the gray values, but showing the detected particles according to their size, the equivalent circle diameter. And I have created two classes assigned a certain color, and it allows me here to define a range to set minimum and maximum values for the classification. So to have the 5 nanometers in the middle here and to have the 10 nanometers in the middle here. The only thing I need to do to switch to new results is to count again. And now, aside of my object measurements, I have also class measurements. And now I see directly the mean values of my red and my green class. I can rename them to make it more obvious for me, also for the later use. And I can get the counting here belonging to both classes and to see how my results are. Having a look onto the total results on my image, they are now identifiable by the color. 10 nanometer gold is green, 5 nanometer gold is indicated with the red color, but I also see still some white areas here, which is a class of particles that does not fit in any of the defined classes. So it does not fit with its criteria to the 5 and 10 nanometer gold. And here you see they are simply larger in size, or they have an irregular shape. They are not calculated in the detection process. So basically it could be fine like it is, but my goal would be to clean it up a little bit to have a real, also for documentation, a clear detection here. So the next goal would be some fine tuning. And this is achievable by using object filters. It can be a very powerful tool to limit the detection process to only objects you want to count later on. And you can use every particle parameter you have defined before for this kind of filtering. If switching back to my results and measure sheet here, we had the object measurements before, we had the class measurement. I'm going now to object filter, which can be simply activated here by this icon. And now you see all my previously selected particle parameters listed here. And I can now set minimum and maximum values to filter out some misdetected particles. Also here, I always see my histogram plotting the number of particles found for a given ECD value. I can define this by two different ways. One is just to click on this icon here. My cursor will jump into my image and I can define now, I can select an example particle that should define my new borders, the minimum value, and the same for the maximum value. And in the same way, I can use, in addition to that, criteria for the other filters. And you see here, I choose also the shape factor because I recognized on my previously shown image that most of the misdetections had a very irregular shape. So I can just set a minimum value for the roundness to exclude these kind of particles. I can rerun my process and you can see I cleaned up the display. All these particles are now filtered out of the image. So that can be a really successful tool to improve the results. I would like to show you another tabulator here, which is showing the class results not only in a sheet but also in a diagram. Both the sheet and the diagram can be saved separately. I forgot to mention that if you run a particle detection on the image and you save the image, all these results are saved together with the TIFF image, which means if you reload the image, you can directly continue working on the image at the moment where you stop working on it. So everything which is displayed here, the classification, the filtering is part of your TIFF image, which allows you to continue your work or to reload it at every given time. Right, there's another option to do some fine-tuning on the image. You can edit your objects interactively, which means, for example, you can auto-split selected objects if they are still stitched together, and you can see by your own judge that this should be separated particles, and you can also delete single misdetected objects. Sometimes it's faster than finding a nice rule for it. And on specific purposes, you can also create a region of interest out of a detection, which is a very specific case of particle detection. Right. All this were really preparations, work on your results so that you can achieve your perfect results here. There is still a tool for you available to verify the detected objects. So to check if, let's say, dedicated particles you see which looks a bit crazy should be included or not. And this verification can be done by two different ways. The first one is here. It allows me to click onto a given particle in the on the image, and you will see the respective result in a sheet. There is a particle sheet link, and you can do it vice versa. You click here on the other icon. You can ask to pan and zoom to the object, which will do the opposite. You double click on a result in your sheet, and you will see the highlighted particle in the image. This gives you a very accurate option to verify the results and to be sure that all detected particles are or should be part of your detection process. If all this is finished, you can use the export button, and you can export the sheet as a CSV file, a comma-separated value, which gives you a sheet which should be compatible to every kind of statistical software. Right. So I would say this could be fine. You got your results, you have saved it, and everything is fine. But you can do, if you like, even some further analysis. You can work with regions of interest, the so-called ROIs. It allows you to compare results within images, especially nowadays where you can grab huge images, for example, by stitching them. Could be a very successful approach to compare between different areas on your image. For example, if you have the situation of different compartments on your tissue. A region of interest can be defined as a rectangle, as a circle, but also as a freehand polygon. I have created here, as an example, 3 different regions of interest, identified by its own color, so that later on you can link the results easily to the respective ROIs. The only thing you need to do here, instead of count and measure, you have a count and measure on the regions of interest. Oh, sorry. It's this here. And you get the same class measurement results here, but now the measurements are splitted and they are shown here for every single ROI. So here now you can see what is the situation in ROI 1 compared to ROI 2 compared to ROI C. For example, ROI 1 has a lot more 5 nanometer gold labels compared to the 10 nanometer gold labels. Whatever that means for your experiment, it's just another level of the analysis of the resulting data. Right. So I hope this was an interesting tool for you to see what is possible with a threshold-based particle detection process. We were using a first step to detect the particles, was to use a threshold within the image histogram to specify the range of gray values which should be detectable. So very decisive step. Define a certain gray value range as being the foreground, and the rest is for the software just background, and it's not detectable. Second step was to specify the way objects should be detected and to select the right parameters for your result. The final step was specifying the way the results should be obtained, calculation on region of interest, on a frame, on the whole image. And I showed you some tools for the fine-tuning that might be necessary to really restrict the results to the wanted objects. If you have questions, if you're interested on the more technical information on our products, the cameras, for example, or if you're interested to have more information on the features of the Radius software, or just if you would like to come in contact with us to let us check if your images could be suitable for such a detection process, please feel free to come in contact with us. You will find us on our website, but you may also contact Media System Lab to discuss the needed questions. I will hand over now back to Matteo, who will guide us through the parts of the question and answers. Thank you very much for your attention so far.